Hey good people, welcome back. In this video, we're going to learn how to use graphs and tables to evaluate limits. So we're just going to start off with the definition of a limit. This is from the website mathsisfun.com. A limit is a value we get closer and closer to, but never quite reach. For example, when we graph the function y equals 1 over x, we see that it gets closer and closer to 0, but does not ever quite get there. We then say as x approaches infinity, then 1 over x approaches 0. And we write it like this. The limit as x approaches infinity of the function 1 over x is equal to 0. Now, this is important notation. Notice they didn't just say that 1 divided by infinity is equal to 0. Even though your intuition kind of tells you that that might be true, you can't actually treat infinity like a regular number. I can say 1 divided by this is 0.00000000001, which is pretty close to 0. But if I were to actually treat this as a valid expression, I should be able to multiply both sides by any number really, and if I multiply both sides by infinity, I would get this would cancel. I would be left with a 1, and 0 multiplied by anything is 0. Well, since 1's not actually equal to 0, that's why this all falls apart. You're not really allowed to do that. So we invented this other notation that kind of lets us explore the idea of what happens to functions as they get close to infinity. Here's another definition. This is from your pre-calculus textbook. This is still sort of an informal definition. There's a much more advanced definition of limits that's included in the calculus textbook, and I attached that to this post as well, that section on limits. You can see what that is. It has something to do with this epsilon delta theorem, and it's way beyond the scope of a high school course. But here's our definition. When we write the limit of x approaching a for the function f of x is equal to L, we mean that f of x gets arbitrarily close to L as x gets arbitrarily close to but not equal to a. This is a pretty informal definition of a limit, and we've actually kind of used limits all year when we describe the end behavior of functions. We would say that for, I don't know, this function f of x equals x squared, we would say what is the end behavior as x approaches infinity, and we would determine that just by looking at the graph that since the function opens and goes up to the right infinitely, that this approaches infinity. Now the book actually makes a distinction here, and they say that a limit can really only equal a finite real number. So technically we shouldn't say that the limit of that function is equal to infinity, but rather approaches infinity. So as x approaches infinity, the limit of the function x squared also tends towards infinity. It increases without bound. And again, the reason they don't like to say equal to infinity is because infinity is not a number, it's more of a concept, right? There is a more strict reason why you're not allowed to have it equal to infinity, and it's based on that other definition of a limit with the epsilon delta definition that you'll see in the calculus textbook. But for now, let's just say that the limit for the function x squared as x approaches infinity also approaches infinity. It increases without bound is the terminology that your pre-calc book uses. All right, so here are a couple quick examples. What would the limit here equal? Well, you can actually explore this by putting in a number really close to 3, like 2.9999, and you'll see that this approaches 5. You could look at the graph of this function here. As x goes to the right, you can see that the y value approaches infinity. And for this function here, as x approaches infinity, the value of 1 divided by x approaches 0. And we're going to do a few examples with one very specific function today, this function right here. We are going to explore a couple different limits. Notice that this rational function does have a couple points of discontinuity. Remember that you're never allowed to divide by 0, so the numbers that are domain restrictions are 3 and 5, because if you put in 3, you would get undefined, and if you put in 5, you would get undefined. Notice here in my table, they kind of have that error there when x is equal to 3 and when x is equal to 5. So these are two interesting areas that we might want to investigate around. So I can't say what is the function equal to when x is equal to 3 because you get an error. But I can say what is the limit of the function as x approaches 3. But first, let's do one where we do a limit as x approaches infinity. So as you go infinitely to the right, over here, what is the value, the output, getting closer and closer to? You might be able to see it on this graph. I'm going to show you a larger version of the graph. As I keep going further and further to the right, this red part, this function, is getting closer and closer to the x-axis. It's never quite getting there because it's a horizontal asymptote, but it is approaching 0. And we can just say that this is equal to 0, this limit. So this is an example where the answer is a finite real number, and you could say the limit exists. The limit exists, and it approaches 0. Another example, let's explore this function as x approaches 5. We see here in our table that when x is 5, you get an error, and that's because if you plug 5 in the denominator, 5 minus 5 is 0, and you're not allowed to divide by 0. But in order to explore what happens to this function as x approaches 5, we can kind of look at some values near 5. So I made a little table here. Some values near 5 are listed. 4.9, 4.99, 4.999, 4.999, 9999. We're getting closer and closer to 5. So as I'm getting closer and closer to 5 on the left side of 5, you can see that this output is getting closer and closer to 0.5. All right, now let's explore what happens as we approach 5 from the right side. All right, as we get closer and closer to 5, 5.1, 5.01, 5.000 or 5.001, 5.0000001. This is getting closer and closer to 4.99999, which is really close to 0.5, right? So because it approaches 0.5 on both sides of 5, we can say that this is equal to 5. This limit exists because it approached the same number on both sides of that number. The limit exists and it is equal to 5. You can also really verify this graphically. As we get really close to 5 on the left side of 5, this is getting really close to this value right here, which if you trace back to the y-axis, it's about 0.5. And you can see that as you get really close to 5, approaching from the right side, we're still approaching the same number as our output. The y-coordinate here looks like it's about halfway in between 0 and 1, which is 0.5. So this should say 0.5. I don't know why I had 5 written there. So the limit of the function as x approaches 5 is equal to 0.5. All right, now let's investigate that other interesting spot on our graph, this vertical asymptote at 3. Let's find the limit of the function as x approaches 3. So you could see from the graph that there is something weird going on here as x approaches 3. From the left side, it goes down infinitely, and if we approach 3 from the right side, it goes up infinitely. They're not approaching the same number. Going down infinitely is tending towards negative infinity, and going up infinitely is tending towards positive infinity. And this is also illustrated in this table here. As I got closer and closer to 3, you can see my outputs are getting closer and closer to negative infinity. Negative 10, negative 100, negative 1,000, negative 10 million. Now, as I get closer and closer to 3 from the other direction, my output values are getting closer and closer to positive infinity. Since they're not tending towards the same number, we actually say that this limit does not exist. So this two-sided limit, when I evaluated it from the left side and the right side, they were not approaching the same value, and therefore the limit does not exist. Now you can actually answer the question, what value is the limit approaching if you just explore the left side or just explore the right side? So we're going to do that now. So the ordinary limit, the two-sided limit, that did not exist. Does not exist because it approached two different numbers. It approached negative infinity and positive infinity. But if I just answer the question of what is the left-hand limit, which means approaching 3 from the left side, we're looking down here. As I get closer and closer to 3, this is getting smaller and smaller in the negative direction. This is approaching negative infinity. And let's do the right-hand limit. So this little notation here means we're approaching the value 3 from the right side. We're getting closer and closer to 3, but this time from the right side of 3. Well, it's increasing, so it's getting higher and higher. It's approaching positive infinity. So this one that's circled in blue is called the ordinary two-sided limit. In this case, it does not exist because it goes in two different directions. But if you just answer the question for the left-handed limit, the left-hand limit of this function as x approaches 3, it approaches negative infinity. And the right-hand limit as x approaches 3 from the right side approaches positive infinity. All right, that's all for this video. I want you to read some of the web page that I attached to this Google Classroom post. It does a really good job explaining the left side and right side limits, and it gives 10 examples at the bottom that you can try on your own. I think that's the best thing to use for this. Also going to upload the chapter 10.3 from the pre-calc book and the chapter from the calculus textbook that's related to limits. But I think the best thing for you to look at is this Math is Fun webpage that's included in this Google Classroom post. We have a video meeting later this afternoon. I'm looking forward to seeing you there. Please ask some questions during that time, and thank you for watching.